Wasabi, you guys. Welcome to Integration Bee Training for Advanced, and this is part 14.2. In this section, we're going to do Cosine Lobachevsky. What on earth is that? So, if you remember our three conditions for Lobachevsky, it just needs to be Riemann integrable at 0 to pi, not 2 pi, pi over 2. Okay, so it just needs to be integrable at 0 pi over 2 in general. And then our second condition was periodicity. Pi minus x is equal to 2 x. So f of pi minus x is equal to f of x. And then for number 3, we just need it to be an even function. F is even. Okay? So now, what is cosine Lobachevsky? So cosine Lobachevsky is different. Let's say you have a function, but it doesn't satisfy this. So apparently this does not get satisfied. Okay. However, it satisfies f of x plus pi, and this is equal to negative f of x. Okay? Because remember, cosine, right? Pi minus x, this equals, negative cosine of x, right? If we apply the same thing for pi plus x, right? Let's see, if you apply the cosine law, right? What's cosine pi? Negative. So we get negative cosine of x, and then same plus 0. Yeah, so this comes out negative cosine of x as well. So, because of that, if we have a function like this, then what we do is we have another property where instead, if you have a function that has this type of periodicity, well, kind of periodic, I wouldn't say exactly periodic, but it has that negative sign. So then this integral is equal to from 0 to pi over 2, that's a 2, and then we have f of x, and this time it's times cosine of x dx. Okay, so if you have a flipped sign for x plus pi, then you have a times cosine of x dx. Okay? So now let's go ahead and apply this. So we have this integral here. How do we do Lobachevsky? So, we already see that we have sine of x over x, and we have cosine of to the power of 5 dx. Okay, but it doesn't satisfy the property 2 that we had, right? It doesn't satisfy the property of f of pi minus x equal to f of x. It does not. It becomes negative. Okay, so if it's a negative version of that, then that must mean something, right? What about x plus pi, right? If you put in x plus pi, you also get the negative version of this as well. All right, cool. Then we'll do the cosine Lobachevsky instead. So now we go ahead, apply the cosine Lobachevsky, and we end up with cosine 6x, right? It's the function times cosine of x. And now, Wally's product, pi over 2, and 1, 2, 3, 4, 5, 6. This is now what, 15 pi over, oh, I'm sorry, that 6 has a 3, so that cancels out. So 2, so 5 pi over 32. So that is our answer. So this integral is equal to 5 pi over 32. Okay, so another way of using Lobachevsky, if the periodicity, instead of f of x you get a negative version, consider this. Consider using cosine Lobachevsky. Okay? We have a weird looking one. I'm going to make this our last integral, because cosine Lobachevsky is actually not that common. But it's just something just to be aware of. So, what on earth is this? We have 0 to infinity, we have x out of nowhere. Okay, let me format this in Lobachevsky form. Okay, because I want to know what on earth is this. We have e to the negative secant square, and we have secant cube dx. Okay. So, I mean, this is technically 1 over cosine of x. This is 1 over cosine of x. Is this Riemann integrable? Right, if I go from 0 to pi over 2, is this function integrable? Right. Well, I don't know if that's integrable. First off, it is a even function, so 3 satisfies. For number 2, is it periodic? Not in a way that we want it to be, right? So instead, it doesn't satisfy the pi minus x, but it does satisfy this. So we'll use that instead. So that means that we'll be using cosine Lobachevsky. So if we're using cosine Lobachevsky, then that means that this will end up being secant square instead. Now, is this integrable? Yes, it is, because we've done this. We've done this integral before, right? This is integrable because this was a Gaussian integral, tangent square plus 1. Right? We've done this before. Right, so like I said, it doesn't have to be continuous, right? This is definitely not a continuous function because it has cosine x at the bottom. So, but it is Riemann integrable. So, because we can't integrate this, we go ahead and use cosine Lobachevsky. This just goes, this becomes, well, 1 over e, 0 to infinity, e to negative u squared du, right, where u is equal to tangent x. And now our answer is square root of pi over 2e. Okay? And that is our answer for this integral. Okay, so that's cosine Lobachevsky, right? If the periodic property doesn't work, but gives out a negative version of it, consider using cosine Lobachevsky. Okay? Alright, that's it for this section. It's going to be a short section, just these two integrals, because it's not a common case that will come up, but just a good thing to be aware of. Okay? Alright, I hope that was helpful. Definitely practice that. Thank you so much for watching, and I'll see you guys in the next part.